Hello again. Tonight's topic is energy from nothing. I know nothing from nothing doesn't work, but you'll 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 find out when you start listening to the presentation what I'm talking about here. So what brought this up was I was watching YouTube videos again. I know that's a dream for some and a nightmare for others when they realize I've been watching YouTube videos. And I started to connect dots. Oh no, not again. Yes, it's me postulating once again. So strap in, ready your tinfoil hats. The usual disclaimers. I'm not creating any new science. I'm just using what's out there. I'm not diminishing any existing principles of heroes of the past that you've long held admiration for. So I'm not changing any of their facts. I'm just adding stuff together. The things that I list up as postulations are earmarked as bold, sometimes red text as postulations. Means they don't have the substance, the math background to say it's a theory, it's not a law. You know, much like gravity's a law, but you can disobey it at your will. And I'll try and stay clear of the popular trigger phrases like quantum vacuum energy, quantum gravity and singularities, 0-point energy, and as from Stargate SG-1, 0-point modules. So you might ask, what has this got to do with astronomy? Well, it has a lot to do with it, considering all the stuff in astronomy that needs power, needs electrical power, and how we get it. We have batteries, we have solar panels, we have things that burn in order to make energy. We have radioactive decay that we use on deep space probes to make electricity when we can't get solar panels to work because they're so far from the sun. And I thought we absolutely need a better way of producing electricity that costs a lot less to make the generator and then doesn't have a periodic bill for the power that you're using. So I wanted something that was essentially inexhaustible, that never needed charging, never required a battery replacement, might be smaller, and that needed no consumable fuel. So those are the requirements. As the saying goes, it takes energy to make energy. And that's true. Currently, we have to burn something. We have to move it in the case of hydroelectric, moving, or tidal or wind. Energy has to transfer. Solar panels, we take photoelectric energy or thermal energy and convert that to electrical. Or something has to decay. You produce heat from decay of plutonium in order to make electricity. Or the material has to be under high heat or pressure. We can get electricity from hot water coming out of the ground. Or the force has to be repeatedly applied. There's this thing called piezoelectric effect, where if you rattle crystals at the right angle, they'll produce small amounts of electricity. And if you look at modern digital scales, that's actually what's happening. When you step on the scale, you're exciting some crystals that produces electricity, and there's some software in there that converts the amount of electricity as a ratio to your weight. And they've calibrated it. And so there's no more spring scale kinds of things. So that's the typical slim profile where you just step on what seems to be a flat plate and you see a weight, or you have a measuring scale for your postal scale and it doesn't spring up and down. There's no springy effect to it. There's no like gear move, lever arm moving back and forth due to spring energy. But that's piezoelectric. And there is another source of energy, and it's always there. It's abundant, and everywhere you look, it's there. The problem is we have no currently defined commercial means of extracting that energy. I'm not talking about solar. I'm talking about quantum foam. At the very, very, very tiny level, you have something called quantum foam, also known as space-time foam. In a vacuum, it's not really a vacuum. even what we think of as a really good vacuum, or even the vacuum of space, it's not truly a vacuum. Even if we remove all the molecules and atoms from a container, there's still stuff in there. It's called quantum foam. Quantum foam is virtual particles, electrons, photons, that literally pop into existence, exist for a very brief period of time, and then pop out of existence. They carry various things in and out of the foam, so quantum foam. The analogy is,
the other name for it is quantum fluctuations.
yes. The other thing is, if you want to think of it as an analogy, think of it as if you look at the top of your beer glass and you see bubbles, the bubbles are different sizes and they're coming and going all the time. So foam. Now, these short-lived particles, technical term here, the electron photon invariant mass related to energy is 511,000 electron volts. And if you remember, an electron volt is very, very, very small amount of voltage. So even 511,000 electron volts is still well less than 1 volt. But that's the energy of one of these particles. A single particle event is very minuscule. You can't do anything with it. But it's always there. It's always present. So if you can gather all this up, it could be sizable. Now, whether or not this is all due to the Higgs field, I'll leave folks at Fermilabs and CERN to figure that part out of it. But I'm just in it for the energy. It exists. It's been confirmed to exist. They do pop in and out after very, very short lifespans, but they exist. So we'll start with, yep, quantum foam should be a great source of free energy if there was only a way we could get the energy converted into something usable. So I stumbled upon this, something called the Casimir effect. This is also at the nanoscale level. They found that if they had two conductive metal plates and they bring them really close together, like 10 nanometers and closer, it would squeeze out all the big subatomic particles. Now you do this whole thing in a vacuum, the best vacuum you can get. So you squeeze out all of the big wavelengths, all the big particles, and the few remaining virtual particles that are left on the inside are smaller. And think about it as you've got big stuff on the outside, small stuff on the inside. So there's going to be an external force trying to push the plates together. So that's the Casimir effect. And I said, well, you have a force, but the force is constant, which means you're not going to make energy directly from this force, because it's like stepping on the scale and then not moving. There's no more piezoelectric effect. You have to have sampled it, and you're done sampling because the force is constant. So this force applies itself in one direction, from the exterior of the plates to the interior of the plates. So if you had something on the inside that could pick up that force as it changed, as the foam popped in and out, you could do that. But if all you do is count on the force from the plates until you start moving the plates around, you're not going to have a delta in the force, a shearing force that will generate any electricity. So yeah, there have been people working on getting power from this effect for a long time. The problem is, to get the energy out, you have to apply energy to it to move it around. And when you move it around, now it can produce electricity. So you've got to use the energy to wiggle it about in order to get the energy out of it, which is counterproductive. But does it really have to be a vacuum? Apparently not, if there's just a significant differentiation between the stuff that's in the plates, which is only the smaller, shorter wavelengths, and the stuff outside of it, which can be all the longer wavelengths, and even particles, even other subatomic particles, and even atoms. You just need a force on the outside bigger than the force on the inside to create the pressure effect. So what if we introduced, let's say, a small amount of very small inert molecules into that space? And if you know enough about something called Brownian motion, when you have a gas, even if you're not doing anything to it, the molecules are moving around. So I picked a particular kind of gas, argon. Argon is something that's inert. It doesn't chemically mix with other things. It's very, very small. The radius of an atom of argon is 0.098 nanometers. So that's like a very small portion of 1/100000th of a meter. So very small, fits within the plates easily. It's plentiful. If you ever looked at the analysis of atmosphere, you'll find that just under 1% of the Earth's atmosphere is argon, which is huge. And it's inexpensive, easy to separate out because it's inert. The only risk with argon is you don't want to have too high a quantity of argon in a closed environment in the presence of oxygen. It won't combust, the argon being heavy and dense, and the molecules can fit close together because they don't interact. It's inert. It will push all of the breathable oxygen out of the room. So the whole of a ship is not a good place to be pumping in argon if you want people down in the bottom of the whole of the ship because you'll suffocate them. So it's safe in small amounts. So here's the effect. There's something called the Pauli exclusion principle that says you can't have a particle that just pops in as a virtual particle and have it occupy the same space as a particle that's already there. It's going to push the particle out of the way and make room for itself. And when the particle disappears, when it pops out, it's going to leave the absence of a density. And you're going to have the particles wanting to clump back together to make up for the hole that you created. So the Casimir effect of the particle coming in and going out is going to produce a very small nudging force. So when the particle comes in, it pushes stuff around. When the particle goes away, it allows things to mingle, which is the opposite of pushing things around. It allows them to disperse. And remember, I added argon at a very low pressure purposefully so something would be there to be kicked around. And the reason for kicking it around is because if there's piezoelectric effect, you have now something that will be kicked around and impact the crystalline lattice and produce a voltage. But there's also something you have to think about, which is at the quantum level, you have this bizarre thing called quantum tunneling. If you have a particle that pops in and you don't give it enough space for it to wiggle around, it will actually penetrate the material if it's thin enough and the plates are close enough, and it will tunnel right through it. So you've got to make sure that the layers you make are at least 4 nanometers thick or large or thicker, and that the gap between the two plates is at least 4 nanometers thick or larger. You want to keep it small so that the argon atoms don't have a lot of wiggle room, but you don't want to make it too small that the virtual particles tunnel through your plates and you don't get any effect from them. So you have to balance out all these measurements. So how do you get the electricity from it? Well, the movement of the particles of argon against the piezoelectric coating says, I'm going to generate some oddball varying frequencies of alternating current. Going to generate basically very low volume radio frequencies. And how do you convert this AC into DC? You use a rectifier. It's a 4-diode, full wave bridge. So you convert the AC variable into a DC variable. But now you need something to stabilize the varying DC into a reliable, consistent voltage. And you have a regulator for that. So if we have the two plates, and if we coat the inside of the plates with a piezoelectric material, something akin to quartz, and then you coat that with a reflective material, something akin to, let's say, aluminum oxide at a very, very thin layer at the quantum deposit, the ion deposition level, you're now going to have two plates that if stuff wiggles around in between it it's going to generate a piezoelectric effect and therefore an alternating current. And you can make these really small and then gang them together, which is what you do with any battery. And strangely enough, Texas Instruments already has a chip, an integrated circuit that does this for you. They originally came up with this in the early days of the Internet of Things. They wanted remotely powered sensors, and the sensors would have to run on like 2 volts or less, and you'd only get a few microseconds before you'd run out of power. So they were actually having little antennas connected to circuits, and the antennas would pull radio frequency from the ambient, like all those radio transmitters around us that are spewing out radio frequency. This little device would have an antenna that would pick up the ambient radio as an alternating current of wide variety, and then they would use this chip to convert the alternating current into a DC current, and they would come away with a usable amperage of PC 2 volts that would last a portion of a second, long enough to take a sample from the sensor. So I said, well, do they still make these chips? It turns out if you have a small solar panel and you want to get a consistent, let's say, 5 volts out of it because you want to use it for USB charging, have you ever seen the solar panels that produce just enough voltage to charge your cell phone? They use these chips to take the strange alternating current, convert it to DC, stabilize the voltage so that it's just the right amount to act as a DC charger for your USB connected mobile phone. You can buy these chips relatively cheaply. Quantity 1, about $5 on Amazon. The circuit board to give you the design of how to do it, you can buy those about $20, quantity 1 on Amazon. So you have a solution that will take in the alternating current and convert it to DC, and will spit out, about 2 volts worth. Well, let's say we ganged these generating chips together and we were able to produce 1.5 volts at 1.2 amps. Very specific number, because there's a very specific thing out there that does that. So we're not getting really power from nothing. It's an interaction that's going on in here, and we're using that interaction to produce a charge in the photoelectric and in the piezoelectric effect, and then we're transferring that to an electrical conductor. So it's not just like one thing doing this. There's a complex set of things that have to interact before you're going to get this output. And if you gang multiple of these together, you get that magical value. If this is so easy, why isn't somebody making billions of dollars off of this? Well, there is already a patent out there for Casimir effect-based power generation. Just remember, just because you get approval for your patent doesn't mean that it's practical or efficient. This particular patent, I took a look at it, and yes, there are sufficient electrons popping in and out of the virtual foam as a power source. Yes, you can do that. It only talks about the electrons. Well, how does it generate them from the electrons? Because it takes the plates and it wiggles them. And the wiggling causes the Casimir to be a shearing force. So the plates are basically doing that, and that's what's generating the electricity. So you have to put power in to get power out, and that's not what I'm into here. The other thing is, while it takes into account the electrons, it ignores the virtual photons. That's why I add the aluminum oxide, so that the piezoelectric plate gets battered by the momentum from the photons. So you've got both electrons and photons. So again, yep, there's a patent out there. He's not cornering the market because it's not practical and it's not efficient. Therefore, it's not a good battery replacement. So the individual cell is conductor on the top and bottom. These are the small cells, not the battery. Conductor on top and bottom, piezoelectric material, reflective material, gap where the quantum foam is. So that's one cell. The gap between the top and bottom should be 10 nanometers or less, but not less than 4 nanometers to avoid tunneling. Around the whole thing, to hold it all together and hold it in, you use a polymer gasket. And remember, the argon is under slight pressure, so it's not a pure vacuum. And then when you make a stack of these things, it's all AC current until you convert it. So it's okay, you don't have to worry about pluses and minuses because it's just alternating current flowing through all of this. And then you can seal it all together and then put the electronics at the top of the battery. And so you have one common set of electronics for a bunch of these cells. So how would this work any better than that patented thing? Well, first of all, we've added the piezoelectric. No rotation necessary. Second thing is we made the piezoelectric thick enough so that we have tetragonal, not cubic crystals. This maximizes the piezoelectric effect. If you make the piezoelectric layer too thin, you get cubic crystals. Cubic crystals don't present pointy ends. And it's the alignment of these pointy ends that when you bounce things against that, you get more voltage out. So boosting that efficiency. The reflective interior allows photons to also push against it. We added the rectifier to convert the AC to DC before it goes to the power chip. And then you use the power chip to take all those weird DC voltages and come out with a nice steady 1.5 volts at 1.2 amperes. So you've got a collective output that's higher and continuous, stabilized. It does not consume power to produce power. You get the virtual photons interacting with the argon atoms to basically hit the piezoelectric material more often and harder. It produces power from both the electrons and the photons. You can gang these things together. A single cell, single one of these cells is 0.001 millimeters. So wafer thin for one of them, and you can stack them together because they start out as AC. You stack a bunch of these together, and the space you have to fit it in is, let's say, a AAA battery size. But you could also think of, AA batteries or those 18650 lithium batteries. There's all sorts of battery sizes you can work with. So let's just say we start small, gang a bunch of these together, and our goal is to produce a typical AAA 1.5 volt battery. What good would that be? Well, on the insides of your average batteries, the thing at the top, that's a 9 volt rectangular battery. Notice it's a stack of cells. You don't get 9 volts out. You get less than 9 volts out. But they glue all of them together in series, so you get 9 volts out. Well, when you need a lot less voltage, let's say 3 volts, you only need 2 cells glued together. That's your typical 3 volt disk battery or coin cell battery. But what if you need a lot out? That's where you get your typical lithium ion battery or the bigger batteries that Tesla's going to be making, the 4680 cells. These are called rolls or Swiss or jelly roll batteries. And you can see the roll, kind of like a toilet paper roll. The particular design varies based upon how much you want out and how much the particular chemistry is producing. So what you want out dictates what you're going to have on the inside. What different layering technology requires different characteristics. In the case of the rolls, it's how thin can you make a single pass of the roll? How much energy are you getting from each layer of the roll? And notice it's continuous. It's a spiral. So if you ever see those, what they call prismatic batteries, those are also layered. They just have Z folded layers, but they're also folded layers. So what about the enclosure of a battery? There's different types of battery enclosures based upon the chemistry that's on the inside of them. The one at the bottom left, that's your typical 12 volt, like exit sign kind of battery, or used in a UPS. They're sealed lead acid batteries, but if the chemical gets out, it's going to corrode things. So they have a nice tight plastic seal and they have little pressure valves on them to keep the pressure as the temperature changes from spewing stuff out of the battery. The next one over, you have prismatic batteries. These are the Z-layered batteries that you've seen in like General Motors vehicles. The next one over is your typical AAA battery that we use in lots of things. The next one over is 9-volt battery. The AAA battery is just basically one cell. The 9-volt battery is a stack of cells. And then you have the jelly roll over on the right. That's a typical lithium polymer battery. So how you seal these things, how you make sure it doesn't leak out, is also based upon how toxic is the material on the outside, how energetic is it. Lithium is very energetic, it's a highly reactive alkaline metal, and what happens if it leaks out? How bad is it going to be? So a non-lithium battery, your typical alkaline battery, has a plastic seal. But if it leaks out, it destroys your remote control. It destroys your keyboard. It destroys your mouse. So wouldn't it be nice to have something that didn't do that? So not only are we generating power, we're generating power in a way that doesn't destroy the device it's doing it in. But how do you get the power out? What are the contact? What do the connections look like? And they're all over the place. On the left, you have a soldered in coin cell battery. This is a battery that doesn't last all that long, might last 3 years, but it's soldered in. So once the battery goes dead, you throw away the entire device and get another one. Some very, very small remote controls are built this way. Cheap, like infrared remotes you might use for an electronic device, they're built that way. The next over is a coin cell battery. Now, why is a coin cell battery better? Because you can remove it and replace it with another one when it goes dead. Makes your device last longer. The next one over is the typical, what they call bump and dent. This is your typical AAA battery, AA battery, where it has a bump on the top and has a slight indent on the bottom. So you snap them into spring-loaded enclosures. The next is that 12-volt battery. It actually has lugs, and you take little spade connectors and you press them onto the lugs. And then the one on the right is the one where you need really secure connections for like spacecraft, where you actually screw the connector on, put a spring-loaded split washer and nut in there to hold the connector in contact so when it gets vibrated during launch, your connector doesn't come off. But I think we'd go with the dent and bump because that way we can use it in existing applications. Here's the characteristics of your typical AAA lithium battery, the kind you'd put in your remote control, the kind you put in your keyboard, your mouse, your pen light, your laser pointer. It's only 1.5 volts at 1.2 amps. If you drained it all at maximum output, you'd get 1 watt hour. So, 1.8 watt hours. So you get 1.8 watts in 1 hour. But you can gang these things together. Typically, you'll have two things in your device, which will give you 3 volts. And they're wired in series to give you 3 volts, as opposed to wiring them in parallel to give you more amperage, but still at 1.5 volts. So this is the sweet spot. If you can find a way to replace these batteries, things are paved in gold, as the saying goes. But if you could find a technology that wouldn't burst like lithium or wouldn't leak like alkaline batteries, that would be even better. So here's a stack of what it would take to do that. The bump and dent, those can be the existing stainless steel, nothing fancy there. They're durable, they're corrosion resistant, it's inexpensive, they're plentiful, fine. They don't conduct electricity as well as other metals, but they're sufficient. Then the individual cells, you'd make them out of a very tough metal that wouldn't corrode, beryllium, which is plentiful. You can get that stuff. It's mined in the US, so you don't have to worry about, oh no, we're giving it to some foreign country. It's very stiff in the presence of a low a vacuum difference pressure. So it's stiffer than aluminum, but it's a little heavier than aluminum. So if you wanted to, you can make it out of aluminum. But it requires high conductivity. Beryllium has a conductivity, this is measured in times 10 to the 6 I forgot the units of measure, something per meter, not stervidians, but Sieverts? No, Siemens. Siemens, yes, named after Siemens. Siemens per meter. So 31.3 as opposed to aluminum, which is 37.7, which is in the ballpark, but you can see the copper is way more conductive than either of those, but it's sufficient. And then the piezoelectric material, barium titanium oxide, also known as barium titanate. It's synthetic, doesn't occur in nature, but it's very good, and you'd make it about 200 nanometers thick in order to get these tetragonal crystals generating the electricity. So I'd say make the layer 600 nanometers thick, 8.5 millimeter diameter plates within the AAA battery. And this keeps the surface area for the quantum phone large. The reflective material, 10 nanometers is fine, aluminum oxide. The exterior of the cell, atasic polypropylene. This is a very unique polymer that's easy to fabricate. It's cheap. It seals very well. It works up to 248 degrees Fahrenheit, so it would work even in space applications. Typical AAA lithium batteries are only good to 140 degrees before they swell up. So it's very stable. So let's say we had one of these AAA size quantum power cells. We need to make sure we make it 100% backwards compatible, volts, amps, output, the whole thing. So if we could do better, pick a different kind of battery. If we can just do this, fine. If we can do much more than this, that's fine too, but I'd say start with this one. If you have other unique applications, make other sized batteries. But this is the sweet spot, the target. This is a power module. This is not a battery. You don't have to ever recharge it. The specific waste heat has to be determined. Remember the electronics for doing the conversion? Those will produce some amount of waste heat. There's no alkaline material here, so no risk of bursting. There's no risk of chemicals getting out. The inner seal is sufficient. There's a reason not to do other kinds of battery sizes initially, because over the entire marketplace, there's very few consumer uses for it. So we'll start with the AAAs. So let's say we can't get to a AAA. Are there things in the marketplace that could probably do with, 1 volt instead of 1.5 volts? Yeah, there's things out in the marketplace. Your average LCD wristwatch has a battery in it. It can run off of that. The 1.5 volts is more than enough. How about the old style hearing aids? They use coin cell batteries? Yeah, they're fine with that. You don't have to have fancy ones. The annual demand for these kinds of products is about 10 million units. So if you could only find a battery that would satisfy these, yeah, you've got a source of revenue. So if you can make a little more, maybe you'll do earbuds or mobile phone earpieces or headsets or microphones. Imagine those never needing recharging. How much would that be worth? Let's say you can make a little more. What would you do next? Smartwatches, mobile phones, laptops. How about medical device implants where you never need to get the battery replaced or recharged? Pacemakers and defibrillators. Implanted infusion pumps. How much more would the patient satisfaction be if you never had to go visit the doctor to have your battery dealt with? Let's say you could do more, like smoke and fire detectors, your average digital security camera. Those don't take that much power. This would be a massive paradigm shift in consumer electronics and medical devices. If you could do a little more, gang up a bunch of these together and do more, handheld tools never need recharging. How much more could you get at a construction site out of tools if you didn't have to put the battery on charge or have multiple batteries so you can continuously work. Other uses, mowers, edgers, hedge trimmers, leaf blowers, and then getting back to astronomy, telescope mounts, drones, surveillance drones. Remember those little batteries that they use nowadays at events? Like I've got 2 of those, the lithium iron phosphate batteries. If you could make enough power to generate that, never need recharging. Battery never needs replacing. Let's say that it doesn't make enough power, but if you could gang enough of them together, then you'd have more than enough power. Imagine if the lower left picture there is a 1, 2, 3, 4, 5, 6. It's a 6 natural gas turbine power generation plant here in Florida. The lake you see in the background is for cooling of the heat from the turbine running. And that's a power generation plant. But notice how much square area it takes up. Imagine instead if you took that square area and you just ganged up massive numbers of these cells. You'd have a power generation facility that needs no fuel, needs no cooling lake. Maybe you could do some buffering with batteries if you wanted to store things off peak, so you could make it even smaller. But imagine a huge power plant that didn't need fuel. What about those solar photovoltaic farms out in the Everglades? Wouldn't need those anymore. So here's the example of a little is a lot. Back in 2006, with those little lithium batteries, they put 6,831 of them in a car, and that's where you got the Tesla Roadster. It had 244 miles of range. Imagine if the batteries that size could be made quantum batteries, you would have a car that you could drive forever. How about the 2023, I picked something newer, the 2023 Tesla Model S Plaid has 8,256 18650 lithium batteries in it. For that, you get 390 miles of range. So the electronics have gotten more efficient, but they put more batteries into it, a couple thousand more batteries. But the instantaneous demand, like when you step on the pedal and it goes to maximum, instead of, let's say, your 100 kilowatt battery pack, you get 760 kilowatts from that 100 kilowatt pack, because you don't do it continuously. You do it for like a couple of seconds, and then you take your foot off the gas because, oh my God, we're going more than 70 miles an hour. So that's the peak or instantaneous demand. If your instantaneous demand was less, you wouldn't need as many batteries. But what you could do is make a hybrid. You could have, for the peak instantaneous demand, you could have some lithium batteries, and then you would put the quantum batteries in to recharge the lithium batteries. So you have a self-charging battery pack. No more charging stations, no more plugging it into wall outlets. You just let the car sit and it refills itself. So if you took the maximum performance and said, my 0 to 60 time is now 6 seconds instead of 2 seconds, I think that's livable. What if the top speed was only 100 miles per hour instead of 200? I think that's livable. So that reduces your instantaneous discharge rate. Well, you wouldn't need, if you could charge in an hour's worth of driving, if you could charge back in an hour, you'd basically be never reducing your battery to 0. So in city stop and go traffic, your consumption is lower and it recharges faster. Or if you park your car in the parking lot when you go to work, or you park it at your house overnight, it's going to be charged up when you get ready to come use it a couple of hours later. Even if it only gets the battery to 75% charge, that's still usable. So no more home or commercial charging stations needed. 0 cost for charging for the life of the vehicle. We've reduced the amount of rare earth materials in the battery. If you wouldn't need any charging connector, you wouldn't need the charging connector or adapter either in the car, at your home, or at work. So that reduces the infrastructure costs. The wiring would get less. It'd be lighter. But ultimately, if you can produce enough power in a small enough space, the goal would be to produce 25 kilowatts at 1 kilovolt. That's a module that would work for semi-trucks, airplanes. You put enough of them together in the same amount of space as, let's say, a nuclear-powered aircraft carrier, and now you have an aircraft carrier that has enough power for whatever it wants to do forever. You could power buses and subways and trams, freight trains, passenger trains, ships at sea. You would have more than enough power, and you wouldn't need that many of these modules to do it. But the real draw here is, imagine if you had a military that you never needed to refuel, never needed to replace nuclear fuel rods, never needed to replace batteries for tanks, ground and air transport, aircraft, submarines, aircraft carriers, their catapults, all the heating and refrigeration and air cooling, all of that stuff, cooking, now has a power supply. Now, what if you transitioned your weapon systems from bullets and shells to particle weapons that only consumed electricity? They'd never run out of ammo, and your military vehicle would never need resupply of even ammunition. You'll need resupply for food for people. Maybe water if you're not converting it from seawater. So you have a far more durable military, because if somebody blows up your nuclear aircraft carrier, you've got radioactive waste. If somebody blows up your quantum battery, it just sinks and no problem. But you never know until you try. So I think that given the hint that the military can make use of this, I'm sure there's people in black projects that are already doing this kinds of stuff, and we're just not hearing about it because it's under non-disclosure with DARPA. But the military industrial complex can do this and then provide it to the military. I think they'd have an infinite source of customers. It's easy enough to fabricate this stuff. The technology already exists for doing it. But the first company that does this, that does it very effectively, they'll publish in journals, maybe get a patent, maybe win a Nobel or something. But the first one that establishes volume production of this stuff is going to be the first money maker. The hardship will be not selling out too quickly to entrenched players like, let's say, Florida Power and Light, NextEra, or battery manufacturers. How many people knew that Duracell was owned by Berkshire Hathaway? Yeah, that came as a surprise to me. And if the military had it for black projects, let's see. I need to find out what the power source is of those orb-shaped or tic-tac-shaped UAPs. This would make a good power source for them. Or you could sell out the technology to a large corporation that already is in need for large rechargeable batteries and has recharging infrastructure. Let's say Tesla or SpaceX. I mean, they want to be an electrical power services provider. This would do that for them. But it would be a massive paradigm shift. So if all you did was replace AAA batteries and maybe AA batteries eventually, all the different things that you've ever bought AAA batteries for that would need now one-time batteries, the companies that, you've got a remote control that you had to buy a new one because the alkaline battery leaked and destroyed the contacts. It eroded them away. You wouldn't need that anymore. The first company that does this in volume would definitely be a billionaire, maybe a trillionaire. That's why Berkshire Hathaway owns Duracell. The companies that make power supplies for computers, for laptops and such, you wouldn't need those anymore. The companies that make the chargers for them wouldn't need those anymore. The companies that make the charging cables, Wouldn't need those anymore. How about the companies that make the vehicle charging infrastructure like ABB? Wouldn't need those anymore. Once you scale them up to the point where you could have a home or business that had its own power source, you wouldn't need your power supply company, your FP&L. The companies that make solar panels or wind generators, you wouldn't need those anymore. The companies that make power grid distribution products, the insulators and cables and poles, and there's a company called Southern that's the predominant source of those things. What about the people that install all that stuff? The electricians that do that? Those wouldn't be needed anymore. So you can see how this would be enough of a paradigm shift that if somebody figured this out, they might not want it to come to market because too many gravy trains go away. So in conclusion, this is a postulation, but postulations are what get us from our current plateau to the unknown and maybe correct some prior inconceptions or misconceptions. If a AAA version of this cell works, it'll work 24/7, 365, all climates, regardless of sun exposure. You can bury it if you want to. Doesn't require massive infrastructure like wind farms. Doesn't require plutonium for spacecraft like radioisotope thermoelectric generators need. If all you did was create a AAA battery that would supply the power, trust me, you'd pay $20 a piece for those things because you only have to do it once, never run out. As soon as you could do it on a large scale, the first company that provides that to solve the problem. On a large scale, if you could make power plants that would do this, you could keep the existing grid. You wouldn't have to transition people immediately. But ultimately, I think powering militaries is the best use, not the best use, but certainly the most dominant use of it. The materials are easy enough, but talk about your paradigm shifts. Definitely the return on investment would be worth it. And the only way entrenched power producing companies would win is if the solution never comes to market. I have lots of hyperlinks this time because there was a lot of research needed to pull all this together. Who knew quantum tunneling was a thing or how to mitigate it? Lots and lots of links. Any comments or questions?
Sounds fabulous, but a long way to go.
Yeah.
I looked at it as the individual cell for companies that already do ion deposition. That's part of their business service offering. Should be pretty straightforward to have an engineering model of it if a company really wanted to do it. And even if it only produced, let's say, microvolts, it's so thin you could stack them up and get 1.5 volts out of it pretty handily. So I think there's enough need for it.
How is the power generation? So let's say like an ice cube, you have those receptors that are producing electrical charge, so they detect the image. Are we inputting energy, and what is the balance of energy? What comes in and what comes out?
Well, first of all, you're not putting any energy in. The energy is already there. What you're doing is taking advantage of the fact that the Pauli principle says you can't have two things in the same place. So you're inducing Brownian motion by having things pop in and out. The Brownian motion is being conveyed by the argon, and the argon is impacting the piezoelectric material producing the voltage. So no energy in, the energy is from the movement of molecules, but they're self-stimulating. The power out, won't note it until you try, but even if it's microvolts, the cell is so small, so thin, you could stack up 1,000 of these things inside of one AAA battery.
So are we producing electricity with that effect already?
Like I said, there's already a patent for it. There's already a company that's producing a prototype, but their prototype requires energy to go in order to get energy out. They don't have the piezoelectric material. They just have the Casimir plates, and they wiggle the Casimir plates to produce a voltage. But obviously that's not efficient and not practical. This doesn't require any wiggling. So once I post it out on YouTube, I'll have the people that go, watched it, didn't get anything from it. Also complicated. And then on the other hand, I'll have the people that are going, you can't do that. That's not possible.
Is the Brownian movement enough for producing impact on the piezoelectric crystals?
Yes.
Okay.
If you have an office scale that can measure to 1/1000th of a gram and still produce enough piezoelectric effect to measure that, it doesn't take much. And they're using cubic crystals because those are cheaper. I'm using tetragonal crystals because even though they're more expensive and the cell is going to be thicker, it produces more voltage. So everything that I looked at, I found some way to like not use it as it is, but how do I optimize that? And then go to the next piece, and how do I optimize that?
So basic, it's nothing else than the Brownian effect, or is like the quantum fluctuations are pressuring the Brownian movement to be higher, so it's being detected by the crystals as piezoelectric.
Yes, for the electrons, but for the photons, for the virtual photons, that's why the piezoelectric material has a very thin layer of barium titanate on it, because that will enhance the radiation reflection pressure of the virtual photons. So you not only get the piezoelectric effect by the molecules hitting it, you also get the piezoelectric effect because the photons are transferring their momentum into the piezoelectric material.
Can a piezoelectric material detect photons?
It's not detecting the photons.
Detecting the pressure of photons.
It's not detecting the pressure of the photons. Photons are reflecting off the barium titanate, and the momentum transfer through the barium titanate is impacting the crystals of the piezoelectric material.
Okay.
So you have a multiple layer effect here. And if you don't think that's enough force, the NASA Glenn Center uses piezoelectric materials to measure nano newtons of force. So it works that if you get the right crystal lattice, where the crystals are tetragonal rather than cubic, the fact that the crystals are being pressed point to point into each other generates more voltage. So everything that I picked, how do I optimize it?
Okay, that seems totally feasible.
And that was the thing, is if the Casimir effect actually exists, which it does, if piezoelectricity exists, which it does, if radiation reflection pressure can transfer momentum, which it does, if argon is truly inert, which it is, put all this together, now you have one cell. Now, how do you stack the cells together? You just encase all of them in a polymer vertically because it's an alternating current, and you collect the sum of the alternating current out of it. Now, how do you get that converted to DC? Simple rectifier. How do you stabilize the DC? Using the off-the-shelf Texas Instruments power chip. Where are you going to find a company that's going to make a battery like this? Any knockoff company that produces AAA lithium batteries, because they're producing the vinyl enclosure, the outside shell, and the tops and bottoms. Just takes one
Have
company.
you do you have an idea of how to make like a proof of concept kind of first thing?
Do I have any idea to do it? I don't have the money to do it because you're talking about, let me go get some high purity samples of beryllium and barium titanate and aluminum oxide, and then I need to ion deposition these things, somewhere between 4 nanometer and 100 nanometer thickness.
If you wanted to patent that, you would be able to, or you would be too based on a patent that you read?
No, I've worked patents before, and you can come up with a patent that's an improvement, that's an efficiency improvement or a practicality improvement on an existing patent. It's just you need to reference it. So I could reference this existing patent and then show all the things that were improved beyond it. Once I post this on YouTube, we'll see if all of a sudden a new power cell shows up out of nowhere, or if all of a sudden they took down my video, cause.
Yeah. That can happen.
Yeah. But I will say that sometimes these solutions to these problems just kind of pop in out of nowhere. I'm looking for a solution to, how do I energize it even more? Well, I know about Brownian motion. How do I get a Brownian motion going that won't involve active materials? Well, you use inert materials. What's the cheapest, easiest to come by, most popular inert material? Argon. How big is the atomic radius of an argon atom? And then you got to make all that fit together. So it's problem solving. That's the only thing that I bring is I can connect the dots, and then when I find problems, I go find ways to solve the problems. Genius it ain't.
Is the Brownian motion strong enough to produce piezoelectric photons effect?
Of the movement of the argon atoms, yes.
Okay.
Okay. Imagine trying to get to 0 Kelvin. Have we ever gotten to 0 Kelvin? No, we've gotten to really, really tiny, tiny amounts of 1 Kelvin, billionths of a Kelvin. We can't get to 0 because of this damn foam that keeps popping in and out and adding energy to things. So all I'm doing is I'm tapping into that foam. I'm just doing it on a very optimal basis. They say, can you get the foam out of here because it's adding heat to the thing we want to take all the heat away from?
They really use foam. Whenever I read that, I read quantum fluctuations.
Well, quantum fluctuations and quantum foam, same sort of thing.
Okay.
Yes. If you do a search for quantum fluctuations, you'll probably find reference to quantum space-time or quantum foam, or it's kind of all the same sort of thing. Okay. Well, since we're talking about sidebar topics, I will stop sharing. Okay. Thanks, everyone, and I'm going to stop recording now.